All right, so I'm going to tell you a little bit about some work we've been doing with the South Pole Telescope combined with Chandra and ATCA, and this is now lower redshift, so we're coming back down to sort of redshift 1 to 2. So this is doesn't need to be said to this audience, but there's obviously some challenges to going high redshift with cluster surveys. In the X-ray, the issue is selection goes like 1 over distance squared, and so you're sensitive to high redshift or high mass clusters at high redshift and all clusters at low redshift. And if you want to study cluster evolution, you'd really like to have the opposite selection, where you're selecting low mass things at high redshift and high mass things at low redshift. And so from an X-ray flux limited catalog, you're missing a lot of the progenitors of normal clusters. If you can find those progenitors, the challenge is they're extremely faint, right? And so this is at the lower part here, a picture of El Gordo, which is the most massive cluster in the universe. And this is what El Gordo would look like if it was this cluster here, a low mass cluster at high redshift. In about 100 to 200 kiloseconds with Chandra, you'd get 100 counts and a ton of background. And so it's really hard to do the same types of studies on these high redshift low mass systems with the same technology. And so the solution there is to develop new tools and to ask questions that are answerable with this data. This has been mentioned already, so I won't go into it, but the SD effect is how we're going to select these clusters. And the idea is these clusters are casting a shadow on the CMB. And this is redshift independent. The cluster just needs to lie between us and the CMB, which is definitely going to happen. And so this is the type of sample we get when we do a large survey with a millimeter wave telescope looking for these shadows on the CMB. This is a very biased plot to South Pole Telescope work. I'm sure we're missing a lot of your favorite clusters on here, but the point is that this is mass versus redshift. These black points are the Bleem et al., the first 500 clusters in the 2500 square degree survey. The green points are the second generation SPT pole survey, 100 square degrees. So the point density is smaller because it's 25 times less area, but the sensitivity is higher. So we're going down to lower masses with an upgraded instrument. And so this generates some really nice samples for studying cluster evolution. And so I've been spending kind of the last 10 years of my career studying things in this red box, basically. And so we got Chandra follow-up of every black point in this red box, and that's 100 clusters spanning redshift 0.3 to 1.8. And it's a really clean sample. So there's no bias towards cool cores. There's basically no bias in galaxy properties or dynamical state of the cluster or AGN. It's just a really clean sample at this mass range and this redshift range. And so this is what 8 megaseconds of Chandra data looks like roughly. So this is 100 clusters, all the black points in that red box again. You can see every type of cluster imaginable here. There's some clusters here that appeal to folks that like mergers. Here's a triple merger that's ongoing. Here's a post-merger El Gordo. Here's the bullet cluster, which is in the SPT field. Here's a double cluster with a bridge. There's a nice sloshing cluster up here. There's the strongest cool core in the universe here, Phoenix. And so there's kind of every type of cluster here, ranging from totally relaxed to the most vigorous merger in the universe, the bullet cluster. So it's a really nice sample for studying the full demographics of clusters. And we've done a lot of really cool work, I think, with these data. So studying the evolution of cool cores, the evolution of the dynamical state of clusters, metallicity evolution, which Becky touched on, baryon content, pressure profiles. These clusters were initially observed for cosmology, and so we've put great constraints on omega matter and sigma 8 with these data. And then studying AGN feedback evolution, which Julia Lavacek-Larondo has been working on, as well as some people in my group. So this is kind of what we've done with the clusters in that red rectangle so far. And when I give this talk at conferences, people always say, well, this isn't apples to apples. This cluster down here is not going to evolve to this cluster here. And so all of our evolutionary studies are bogus because this isn't an evolutionary track. And so we've gone back and we've defined a new sample that is based on cosmological simulations. And so the tilt of this green rectangle now matches evolution, right? And so this cluster down here should evolve into this cluster up here on average. No one cluster, follows a diagonal track, but the average population evolves. So these are all the clusters in this green envelope share a common evolutionary track. And the evolutionary track they share is that of Perseus, basically. And so the clusters in this green rectangle will evolve into a Perseus-like cluster. Coma's up here. And so the things we have been studying are coma progenitors, of which we have like one. And so it's tough to do Redshift 0 demographics. There's a lot more clusters like Perseus. And so this is sort of, the title of the proposal was studying the progenitors of our favorite clusters, the Redshift 0 Abel clusters, basically. And so this is work from here on out that's been entirely done by my postdoc Florian Rupen, and so I'm trying to sort of publicize this as he makes his way, through the postdoc track. And so this survey has been 75 clusters spanning similar Redshift 0.3 to 1.5, but again now it's a common evolutionary track, which is the exciting bit. So the challenge is that we're looking at these lower mass things at equally high redshift, which means they're faint, and we're not going to get more Chandra time than we've already gotten. And so the challenge is we have to go shallower on these things to do it in the same amount of time, basically. And so we've been working with 100 counts per cluster, and so that's where the technical challenge lies. And so again, this is Algordo. This is the data quality we are typically getting for our Redshift 1 low mass clusters. And this is if you smooth that data in a clever way, and you can recover that this is an offset core, that it's dynamically active, and that's about it. So you get broad morphology, you can detect large scale asymmetries, not small scale sloshing. You can identify cool cores, you can measure luminosity, you can identify point sources. So there's lots of cool things you can still do with only 100 counts if you spend some time on it. But if you couple that 100 counts with the data you already have, which is the SZ data that selected the cluster, you can actually really bring out more in those data. So here's a density profile. This is electron density versus radius with 2,000 counts. Then if you downsample this data to 100 counts and measure a profile, it's mostly consistent with anything everywhere. So you have orders of magnitude uncertainty in the core and the outer part. But then if you just fold in the SZ data, you tighten up the constraints. And the reason for that tightening up is because you have no temperature information in 100 counts. And so you can have a perfect surface brightness profile, but to convert from surface brightness to density, you need a temperature. And if the temperature is consistent with 0 to infinity, your errors are huge, right? And so, so the idea here is that we use the SZ data to constrain the temperature, which lets us calibrate from surface brightness to density. And so this was sort of a big step forward, and we're basically getting equivalent 500 count data by folding in the SZ information. Okay, so let me use the remainder of the talk to just tell you two quick things we've learned from these data. So, the cool thing I think is this sample and the new data analysis, but let's talk quickly about what we've learned from that. And so at Redshift 0, there's these cool core and non-cool core profiles. The cool cores have very low cooling times, short cooling times in their cores, which is interesting. And we want to ask, how does that evolve? And so if you take cooling time profiles and just add 3 gig a year, 10 gig a year to them, they should change. So as you go back in time, in a very simple model, the cooling time profiles ought to change. And what we see is that they don't. And so we can look at this in terms of the central density. The central density as you go back in time is fixed. There's kind of a maximum density. This could be the sort of precipitation floor that someone like Mark Voigt would talk about. But there's basically the distribution of densities in the centers of clusters is unchanged at all redshifts. And so this upper plot is the earlier work with a fixed mass cut sample. The lower plot now is using the evolutionary selection, where we're selecting clusters along a common evolutionary track. And you see the fraction of clusters with low entropy cores is the same at all redshifts. And so there's no measured evolution in the fraction of clusters hosting cool cores. And depending on how you define a cool core, that fraction is roughly a third. But the point is, once you decide on your cool core selection, there's no evolution that we detect. So that's cooling. We can also look at feedback. And so in the nearby universe, people look at things like bubbles and jets in the centers of clusters to quantify how much energy injection is being, or how much energy is being injected into the medium to prevent runaway cooling. And so in a system like Hydra A, you can see the jets in red, you can see the bubbles in blue, you can directly see work being done on the hot medium. And you can compare the heating to cooling rate, and you can see that this heating is balancing cooling, and that's why we don't have cooling flows. At high redshift, this is really difficult. So this is pioneering work done by Julia Slavicek-Lorondo, and it's the state of the art in terms of high redshift bubbles. But you can see it's extremely hard. I've rotated this so it looks the same as Hydra A to help, but you can see that these are very challenging to detect. But when you do detect them, you find that the heating is again balancing cooling out to redshift 0.6. And so we've tried to expand on this, and we do this by using the in-hand radio data. So we have 100 square degrees with SPT data, with ATCA data, and with pointed Chandra data. And so combining these three things, we can extend this plot out to redshift 1.3. And so we're taking the jet power now from the radio emission rather than the bubbles, and we're utilizing the 1.4 gigahertz P cavity relationship along with its scatter, which is substantial. And the punchline is that we see no evidence in the heating cooling balance at high redshift. And so it looks like AGN feedback, thank you, is it's perfectly capable of preventing runaway cooling flows at high redshift. And again, this is a progenitor matched sample. So all of the red points evolve into the same cluster. They're all selected along a common evolutionary track. The blue points are the clusters that those evolve into. They're typical Abel clusters that are well studied at redshift 0. And so this purple fit is, this is still a work in progress, but this is probably the final version of this plot, and it's consistent with no evolution at all in that heating is balancing cooling out to at least 9 billion years ago or 8 billion years ago. So I'll just summarize here with a couple of things. So first, this is a beautiful sample for studying the evolution of the intercluster medium. I've touched on just the heating cooling balance, in 12 minutes, but there's a ton of really cool things we've done with this sample, studying enrichment history, thermodynamic profiles, dynamical state, and so I'm happy to talk about any of that. And the real, push we're making right now is to not just go to high redshift, but to go to high redshift and low mass simultaneously, and really study the progenitors of a system like Perseus or Abel 2052 or Abel 4059. These classic low redshift clusters, so we can do an apples to apples comparison to the enrichment and cooling flows and heating and all of these fun bits of physics. So I'll stop there and take any questions.